everyone. Today we have Javier Blanco Cordero
Yes.
and Patrick Mira. And the title of the talk, well, the most heartbreaking demo ever. So a little bit of bio of our two speakers before I let them hold the floor. So Javier Blanco Cordero is a senior data scientist at Quix, where he helps customers to get the most out of the data that they have. And Javier is a master, lecturer, and speaker specializing in pragmatic data science and causality. Patrick Mira is a co-founder and head of software at Quix, responsible for the quality and technical approach given by the software development team. Patrick has led multiple development software in very big companies and organizations for over 2 decades. So please put your hands together and give a very warm welcome.
Hi, everyone. And yes, welcome to the most heartbreaking demo ever. Or we are going to see today how to work with real-time data. But not just any real-time data. You can see maybe there that I'm wearing a heartband. This is monitoring my heartbeat. So we are going to see today how to work with my real-time data, hence the title. So for the demo we will be later in this session, we are going to follow a bit of a play role. I'm Javier Blanco. I'm the senior data scientist at Quix. So I'm going to be the senior data scientist, well, the data scientist in this project.
Yeah, I'm Patrick Mira, I'm head of software and co-founder at Quix. I'm going to play the role of data engineer today.
And because we are going to be working with real-time data, we're going to be using streaming technologies. So we are curious, and we wanted to ask, how many of you have experience with streaming? So could you raise your hands if you have worked before with streaming? OK, some hands. And what about Kafka? Any of you? OK. So I see most of the room hasn't have experience with streaming or Kafka. And that's perfectly fine, because the next section is an introduction. So what is streaming? What is streaming versus batch? And why it can help us work with real-time data? The typical way to present this is with the river metaphor. So thinking any data flowing as that river that you see over there. So any data system in your company, anything that will be producing data in real time is that river over there. Under the traditional batch approach, what we do is we collect a set of data over time, and then we throw it in our analytics systems. We fill that bucket of water, and then periodically, we throw it in our data lake, where the water is static, and we can process it. Now, under the streaming processing approach, the data is fed into the analytics systems piece by piece. So as soon as we get the latest point of data, we process it. In our river metaphor, it will be like building a pipe, and we process the data whilst the water is going through the pipe. Let's go further in this comparison. So imagine we want to do an aggregation operation. Here we have our raw incoming data. Under the traditional batch approach, we first load that into a database. Then we load that into our analytics systems, and we perform the aggregation operation that you see here. With the streaming, as soon as a new piece of information is generated, we can process it and perform the aggregation. So the advantages here with batch is that when you do your analytics, you have your whole historic data. So if you are training a machine learning model, that's handful. If you are doing a processing for which you need lots of historic data, that's very helpful. But if you don't need that, you are actually spending some resources in storing data that you wouldn't need otherwise. You are also inserting some lag, because you have to wait for some data to be stored there before you process the latest piece of information. We are going to see that in our examples later today, but let's go a bit further in the theoretical introduction. The first level citizen in a streaming architecture is the Kafka topics, or more generally, the message brokers. This is the place where the data is shared. And at one hand of the topic, we will have a publisher. This is a party that writes data into the topic. But this is not a database. As you see, the data stays in the topic available for consumption for a while, then it's not there anymore. At the other side of the topic, we will have the subscriber. This party is consuming, is listening to any data that is on the topic. And the other great characteristic of these systems is that they are completely asynchronous. It doesn't really matter how many publishers we have or how many listeners, it's going to work. It doesn't really matter at which rate the publishers are writing the data or the listeners subscribing to it. With a buffering system, it's going to work. Great. Now you understand the very basics of streaming. So, Patrick, can you tell us about the approach we will follow today?
Yes, thank you, Javi. So now that we know about the streaming a bit more, so let's talk about a bit what we are going to show you today in this demo. So what is our approach? So we have three main ingredients for the demo of today. So we are going to use microservices. That it means that we are going to encapsulate different parts of our streaming application in independent processing units. We are going to use Kafka as our message broker. That it means that it's going to be our main way of sending and receiving data between the parts of the pipeline. And we are going to use Python as a main language to develop these microservices. And while Python, well, because Python is a very user-friendly language and many data scientists use it for data processing applications, we have more languages in the system, but today we are going to use Python. Let's talk about a bit of the streaming architecture itself. We are going to use today a streaming architecture, but before let's see the difference between a traditional batch architecture compared with a streaming one. So in a typical batch architecture, we would have the following approach. We would save the data directly from the source into a database. Then we would read the data to process it with some well-known processing batch platform, and then we would send it back the results into the database again. So finally, maybe we want to consume this data externally, and again, we would read the data from the same database, asking periodically for new data. And so as you see, the database is our main medium of transportation of the data, but this looks a bit incorrect because a database is not designed to be a medium of transportation. So it's designed to store data forever, or maybe for some time, but not to be a medium of transportation. But we don't need to save this data forever in our case. So in reality, what we need is something that maintains the messages in memory for some time before we process them, and that's it. So what we are going to use is a message broker, because a message broker is designed to do exactly that. It is also designed to do it very, very fast. But this doesn't mean that we are going to remove completely the database from our architecture. We're just going to put it in a side, because at some point it could be very useful in some parts of the development, as Javi is going to show you in a moment. Okay, so for the demo of today, we are going to use Quix. What is Quix? Quix is a developer platform to help data engineers and data scientists to create streaming applications. For instance, the same demo that you are going to see today, without using Quix, you would need to probably some weeks of development to arrive to the same result that we are going to arrive today. So let's talk a bit about our background. So the idea to create this platform come from our previous experience working in motorsport. We were working in McLaren, developing a streaming processing platform, sending data from F1 cars to the factory. We were processing this data with some machine learning models and some simulation simulations in parallel in the cloud, and we were sending back the results to the track again, all in less than 1 second of latency. So it was quite complex and quite challenging use case because we were sending nearly 1 million of values per second, but it helped us to understand the level of complexity that requires a real-time processing application like this. So let's start the demo. So let's start sending data. The first thing that we are going to do is to ingest new data to our system. For that, we are going to use this phone. So this phone is generating some data with its sensors, and it is connected as well with the band that Javi has on his chest. And this band is measuring the heart rate in real time and is sending the values to the phone. And the phone has a very simple application that is reading the data from the sensors and from the band and is sending all the data to a topic that Javi has explained now using one of our APIs. So let's see if we are receiving data into the topic. So let me change to the application, to the platform. Yes. So here is the topic that Javi was mentioning before. So it's the phone data, and we see that we are receiving some data here, data in and data out. And let's explore what we have inside this topic. So we have a stream that is basically this device. Javi Xiaomi is the phone of Javi. And we have some parameters. And if I select G-forces, because Javi is moving around, we see some data in real time that is moving. No, sorry. It is the sensor of the phone. So if I move the phone, we see the movement. And if I let it stop it, it's not moving. If I move it again, so it's real time. Okay? So let's change it to the data that we are interested today. So we are going to work with the heart rate of Javi. So let's change it to heart rate, and let's see how nervous Javi is. Yes, so.
Yeah, it's only going to go up now that I know
90.
you're looking at that.
It's a lot. 92. So Javi is normally is in 60.
Yeah.
No?
Yeah, I'm normally a calm guy, but.
So let's start working with this data, no, Javi? So
Yes, thank you, Patrick. So, as a data scientist, Patrick has done for me everything that I need. He has created this ingestion system. So you see there data coming in real time. Let's have a look at the slides to see what he has built. Basically, again, this phone is sending the data to what we introduced earlier, these Kafka topics. So the data is going there piece by piece in real time. Something we didn't mention is that we are also storing that data, in this case, in a database. Let me show you how. So if I come back to topics, you see that phone data 1 has persistence enabled. That means I can access the historic data, not just the latest points as Patrick was showing. So I'm going to go to persisted streams, select phone data, and then this is now today. I'm going to visualize that. I'll take out aggregations. Now, this is showing the data, obviously following my Spanish time, but still, this is showing the data of my heart rate for the last 40 minutes or so. Can you guess when I started speaking? And when I'm back to speak? So yeah, this is just a way to look at the historic data as we will do with any other system. But if, as a data scientist, I want to do more, I can always query this data. I'll come here to code, copy that, and because I'm a data scientist and I love Jupyter notebooks, I'm going to come here to my collab, paste that code in there, and execute that. And what you see there is the same data we were looking at, but in a data frame. So I'm now able to do anything with this. Like here, I'm going to change the timestamp format to data time. Here, I'm going to look at my histogram. So that's the distribution of my heart rate. Or I have this function here this is going to be inversing. This is going to compare my distribution heart rate now to my distribution when resting at home. So that's me at home, below 60 on average. That's me here, well, like doing exercise. So, well, what you see here is that we can really have a look at the historic data as we will do with any system. This is the traditional batch approach. You query a database and you work with that. But as a data scientist, I'm going to try to do a transformation with this data. And what I'm going to do today to try to add value to this data is to calculate the calories that I'm burning in real time. So using the heart rate data that Patrick has just ingested, I'll try to calculate how many calories I'm burning. And by no means I'm an expert in calorie burning, but I did some little research, and there are these two main ways to burn energy. One, the base metabolic rate, is just by keeping alive. So thermoregulation, respiration, blood circulation, all those inner processes that we need to keep alive, well, they are unintuitively expensive. We spend most of our energy there in the base metabolic rate. And then we also spend some energy moving. Now, let's not go into details, but this Noakes-et-al formula that we see below takes into account both the base metabolic rate and the movement to give you an estimate of the calories you burn over a minute, given an average heart rate. So I'm going to use that same formula there. I'll go back to Colab to try to calculate the calories that I'm burning. So I'm going to go back to my Colab, and let's have a look again at the format of the data that we have. So really, timestamp and heart rate. Because this Noakes-et-al formula estimates the calories over a time period, specifically over a minute, I'm going to first calculate the time deltas between each timestamp. That's really simple. You see, I'm basically doing current timestamp minus the previous one and getting that in seconds. So there are 4.3 seconds between those two timestamps, but 1.1 between the next ones, and so on. And then I'm going to calculate the average heart rate between each of those data points. Again, just a window type of operation where we calculate our current heart rate and the previous one, and we do the average of those two. And now that I have a delta time and an average heart rate over that delta time, I'm able to calculate the calories that I've spent in that delta time. For that, I'm going to use this function. As you see, it's the same formula we saw in the slides. I then calculate proportionally, because again, that formula is per minute, so I just do the proportion to see for the time delta that we send how much calories we've spent. And now I'm going to add a new column to the data frame. It's going to be called cal, from calories. I'm going to be using my newly created function. And you see there that for the heart rate parameter, I'm passing the new interpolated heart rate column. For the time delta, the new delta time in seconds. And then that's my oxygen consumption when resting, that's my weight, and that's my age. So with those, voila, there we have our new column. So that is showing us that 0.3 is the amount of calories that I spent between that timestamp and that one. And that there, for instance, is the amount of calories that I spent between that timestamp and the previous one. If I now do an expanding sum of that, I will get the total calories over that data. So looking at the tail, looking at the last point of data, you can see there that I've spent 135 calories over that time. Now, is that correct, you think? Well, it was, but it's not anymore. It was correct when I loaded the data into our Jupyter notebook. Now, since that, I'm still alive, I'm moving, so I've spent some more calories that are not included in that calculation. And that's the problem with batch approaches. So how can we take this calculation to real time, to streaming? Let's just do that. Before going into the platform, I'm going to show you with some slides what we have done and what challenge we have ahead. So now, working with batch, it was pretty easy. We had a whole table, and we performed that type of window operation. So for T2, doing the calculation T2 minus T1 was easy. We have both points of data there. For 3C, the time delta was T3 minus T2. The average rate, heart rate was again easy, that, and we did the average, and we follow a window type of operation. That's simple. But now with the streaming, remember the pipe metaphor. At T1, we are going to have the information from T1. At T2, we will have just the data points from T2. At T3, we will have just the heart rate for T3, and so on. So how can we calculate those time deltas and average heart rate if we only have that piece of point? And that's one of the difficulties of streaming. There are some operations that are much simpler with batch when you have a whole set of data. But we have an open source library. I hope you become contributors at some point. We have many contributors helping make a streaming developing as simple as batch developing is. So one of the library items there is going to do the following. We will select this library item that keeps in memory just the amount of information that we need for our calculations. So what you see in that square is the amount of data that our library item, our microservice, is going to keep in memory. And as you see, that allows us to do the calculation T2 minus T1. Then in T3, we will keep in memory T2 information. In T4, we will keep T3, but not more. That means we react in real time, and we are very efficient with the amount of data that we store. Let's just do that. So I'm going to come here to the open source library that I was referring to. As you see, there are many items there. Some of them are to connect to databases or some sources of real-time data. Some of them are to perform transformations. So I'm going to look for this interpolation item. It does exactly what I have just explained. There you see in the documentation, it really follows the same approach. And what is this interpolation code going to be listening to? Well, it's going to be listening to the pipe of data, to the topic that Patrick generated. It was called phone data. There we are. And what is this going to be outputting to? Well, to another topic, one that is empty so far. For instance, this phone data heart doesn't have anything inside just yet, but we are going to send the data there. Now, for the parameters that we want to interpolate, I know the name is called heart rate, like that. And I could save this as a template, as a project that I modify later, or without writing a single line of code, I could just hit deploy. And this is building a microservice. It's now installing all the dependencies that it needs. And this is going to be an independent microservice working in the cloud, self-sufficient. So let's cross fingers. Check that everything goes fine. I think internet is a bit slow, so I'm going to go here and check that that has been created. It has been created. So there you see our interpolation code working. What you see there is the logs in the console. And check there, this is pretty cool, isn't it? We see our code there. We see the amount of data that is coming in from the phone data topic and the amount of data that is being output to this phone data heart topic. You see that moving live, which is pretty cool. And then we could also have a look at the raw messages itself that are going through. So if I look at the input, which is, again, that phone data topic, I can have a look at some of those values. And you see the format. You see we have that heart rate data. Now, if I look at the output and check any of those messages, look, not only we have heart rate, but we also have the delta time seconds and interpolated heart rate that we needed. So this interpolation transformation is working as we were expecting, But we haven't calculated the calories just yet. So look, I'm going to add a new transformation there that is going to be listening to this phone data hard topic, and this is where we will add the calories. Again, I'm in the library. I'm going to select Python because I like it, and I'm going to use Hello World example. I'm going to call this code calorie calculation. This is listening to the phone data hard, and now it's going to be outputted to another topic. For instance, this over here, hard calories, that is empty so far, but it's not going to be anymore. Now I'm saving as a project so that we can change the code and not just deploy without doing anything to it. This is a hello world example. It's not doing much just yet. So I'm going to bring first the noxetall function. I'm going to bring it from my collab. I'm going to paste it there. So it's defined. I don't need that in this case. And I'm going to copy and paste the code that I need just to make things quicker. But I'll explain it in a second. So what is going on here? At line 22, we are defining what happens when we listen to a new piece of data in that topic. At line 25, we are converting that new piece of data into a data frame, which is a format we all are used to work with. This is traditionally not the case with Kafka. It's quite complex to work with its data. But here, we have the new point of data as a data frame. Then I'm using the same function we've gone through to calculate the calories burned so far. I'm printing that in the console, and then I'm adding that to this new cal column. Now, I'm going to add something new. I'm going to add the total amount of calories. So I'm going to do, in this class, total cal, and I'm going to initiate it as 0. And then I'm going to update this as soon as the new calories are calculated. So every time we calculate a new set of calories, I'm going to update the total amount of calories. Good. And now I'm going to add a new column called total calories, cal or cal tot. So our data frame that came just with the heart rate, the interpolated heart rate, and delta time in seconds, it should have now the calories and total calories. And now outputting this to the output Kafka topic, that again will be a tremendous work, it is just that 45 line using the Quix SDK. So we just say write this df, and that will do. I'm going to save this, this code. As you can see, we have the Git history there. I'm going to tag this version as 1.01, and I'm going to deploy this as a microservice. I'll select the version that I want. I'm going to select the resources that I need, which are not that many, and I'm going to hit deploy. That's building. So again, we are building a microservice in the cloud. And look how interesting this pipeline is starting to look. What you see there is the building blocks that any streaming architecture building Quix will have. We will have some microservice doing the transformations, and the arrows are the Kafka topics. So you see data coming in, this is process, data going out, and now we are building this calorie calculation, which seems already built. Great. Starting to listen, nice. So this is catching up now with the Kafka queue, but very soon it will be up to date. And the numbers we will see there will be the real-time numbers of the calories that I'm burning just right now, which is quite cool. And with that, I think my job as a data scientist is done. I've done a transformation. Do something with our data.
Yeah, thank you, Javi. So, okay, now that we already have this heart rate data in real time, let's do a final step, that is sending these results of this of this data outside of our pipeline. This could be, in reality, any external system. It could be a database, it could be an alerting system using Twilio, Slack, or whatever, or it could be a dashboard, or it could be all of them at the same time. So it doesn't matter. Today, what we are going to use is just a very simple dashboard using one of our templates, the same that templates of the library that Javi showed you. So let's do that. So I'm going to the home, and let's see what Javi have created here. So I'm going to the destination. This is a, this, as Javi explained, is like a microservice factory. So I'm going to select one template that we have here is called dashboard, real-time dashboard. And so for today, I'm not going to use this part of the code. So what I'm going to do is just, well, first I need to save it as a project. If not, it's not going to work. So this is the input topic that is correct, not Javi. So save it as project. And yes, from here I don't need this part, because what I'm going to do is just save the data we're receiving in real time, that is this package, into a Panda data frame, and I'm going to change this to data F, and here we are going to send it to this dashboard, data df. And I think that with this template is because everything is prepared, we have the Docker image, we have everything in place, because we can just play run and see if it's working.
Yeah, we didn't mention earlier, but you can develop in this online IDE. We've been deploying the data. That's what you will do when you want to productionize your code. But when you are testing and coding, you can just hit run and really develop in real time.
Yes. So this microservice specifically has some web interface, so it's something that you can access with a URL. So for that reason, we have this link here. So we can see that this dashboard is just a very simple dashboard using Dash library. That, yeah, you can do a lot of things with Dash, but for the demo of today, we don't need it. So yeah, so you can see here in real time in this dashboard the calories of Javi in real time, and there you are. So it's not using any database; it's just using in-memory information. So the performance and the resources spent are minimal compared with if we could use a database. So maybe it's not the most beautiful dashboard, but
it's a really quick one.
It's a really quick one, and it's the beauty of the streaming.
Yes. By the way, looking at the dashboard, we are coding live, and I'm realizing I made a mistake. So you see there that the calories and cal total are the same. And I think this is because if I go back to my project, I did a typo. So in my calorie calculation, when I was defining the cal total, I just left it as calories burnt, when I should have put there the total, right? So actually, I'm gonna change that. I'm gonna save that code. This will be 1.02. Perfect. I'm going to go to the current deployment. I'll stop it. I'm going to edit it, and let's point to the new version of the code. Save. Yeah, this is save. I'm gonna hit run. So at some point, the data we will see there and in the dashboard will become correct. I'm just saying it was my mistake. But yeah, I hope you have enjoyed what you've seen today. I hope you've seen how streaming can have lots of potential in a data science project. There are many places in a data science project where you can use it. For the data sourcing, for the data processing, you've seen it now for creating dashboards in real time. There's something we haven't talked about today, which is machine learning models deployment. Streaming is a great architecture for that instead of a REST API. And Yes, I hope you have enjoyed what you've seen. If you want to give a streaming a try, we have a free trial developer account that you can use. But if you are really going to do that, I recommend you sign up just now, because our colleagues from marketing have prepared this special occasion where you have the double amount of credits. And that really means you will be able to build on your own for free anything you can think of, something like what we build or something far more professional, if you are interested in testing streaming. So that's all from us today. I hope you've enjoyed it, and we are ready for questions.
Then
Thank you.
I have a limited knowledge around streaming, but I know Snowflake is quite a big player in
Mhm.
that thing. So I was wondering how the integration works with the platform because I think it's so connected.
Yes. Do you want to speak more
which
about
connector
the
is?
Snowflake connector?
Yes. Well, we have some connectors already implemented there, and I think that the Snowflake one, it was quite generic. Um, I haven't implemented this connector, so I don't know this specifically. But there is a guy there that has implemented it. Maybe after the chat, we can speak with Peter, and he can explain you about the Snowflake connector.
Thank you very much for the talk. So if you think about capacity and compute power that you need to process this and streaming type of workload against batching type of workload, um, regardless of the time or lag element, if you wanted to have all your data, imagine that you're working on very big data platform processed by, let's say, a fixed point in time, and you need edge capacity to do it on a batch application type of thing. How would the capacity compare to an streaming application?
So I don't know the numbers exactly, but the benefit to do it like this without using a database is that you don't have the input and output operations. These input and output operations into a database it requires a lot of resources and a lot of memory. So on that regards, we are saving this time because we don't need these input and output operations. And in terms of speed, so I think that if you're need to batch, there is a point that you cannot do it with a database. So maybe with some devices, like 10 devices, it can work. But when you start having thousands of devices, or maybe 1 million of devices, the database use case is not going to work. It's not about how much, it's that literally it's not scalable. So I don't know the numbers, but the resources needs for streaming are much less than if you are using a database. Because as I said before, a database is not designed to send messages. It's designed to store data forever. So when you want to send messages and process the data, and it's temporary data, you need to use something like a message broker. And Kafka, in that regard, is very efficient to process data and in very huge amount of data. So in McLaren, we were sending like 1 million of messages per second, and it was capable to that. It was just one Kafka broker, so it's quite efficient.
Have you considered when you are developing the software, have you considered alternative to Kafka? And related to that, in the backend, you mentioned that you are deploying on the cloud. So I suppose you can select which cloud you can deploy for. And
Yes. So we are currently only supporting Kafka, but we have explored another options like Pulsar. That is another broker that is quite famous, but right now we are only supporting Kafka. And when you create a workspace in the platform, you can select to use our managed Kafka or use Confluent Kafka, that is a provider of managed Kafka. But in the near future, we are going to provide more managed Kafka provided like the Amazon one or the Azure one. So yes, for now it's going to be Kafka, and you can select which one you want to use, or if you want to use our managed. But yes, we are exploring another message broker, yes.
Can I ask another question?
Yes.
Sorry, just came to my mind. One use case that I can think of this one is actually for like graduate data scientists or seminars which participate to Kaggle competition.
Hmm.
So have you thought about integrating like an integration in Kaggle platform to fetch data from there and
Yeah.
use it here and then?
We have big ideas, so they may come in the future, but we have ideas around. You know how right now in Kaggle, most of the competitions are around. You send your submission, and let's see what happens. Wouldn't it be cool if you send your model and you evaluate over the next months who is the winner? Like that's something we have in mind, and we will try to propose at some point. We work with universities, and for instance, some of my students did a competition on algo trading. This is really simple for them to do the whole data science project from scratch, from the data sourcing to the ML deployment. And yeah, they compete against each other building algo trading bots. So yeah, there are many things in here about about creating competitions, creating something fun. We also have this idea of becoming the place to go, not for databases, but for real sources of real-time data. So same as you can find in Kaggle historic databases, imagine you could go somewhere and connect to something in real time. So yeah, we have these ideas. And you had a question.
Yeah, I
Yep.
have a question. This platform for streaming seems very cool. Do you have competitors in this area? And if yes, like how you are better than your competitors?
Go on.
I don't think that we have a competitors in the same type of platform, because this is like an abstraction on top of several technologies like Kafka, Kubernetes, and time series databases. So I don't know any competitor. So
I will say what Databricks is to batch, we are trying to build for streaming. So that will be like a competitor, but in a completely different processing type of, in a completely different processing type.
yes, you can compare this like DBT, but for streaming. But yeah, so all the technology that we are using is like an abstraction. We are creating an abstraction on top of that that allow us to be able to change these technologies in the future if it's necessary. So we are creating something that easy to use, but not very tied to any technology itself.
I think there was a question there.
Thank you for the talk, though. It's very interesting. The first slide when you were talking about working with McLaren,
Yes.
is there anything you can do to make it perform better this season?
Yeah. Well, I think that in the motorsport and in McLaren specifically, the software is important, but it's not the only thing that is winning the race. We were helping them to win the race, but there is another factors that enter to the winning concept. But yeah, we will try. Yeah.
Last question, I promise. Your example was with numerical data, heart rate data, right? Do you have like demos or examples on the platform that I will check later on different types of data, like images, maybe, or videos, or text data?
I think there is some connector in the library with image data, but we do have some examples and some demos and videos around textual data. So you can connect to a Twitter feed and do maybe some NLP on that. So yeah, there are some examples around that. There wa-
Yeah, I was wondering, you mentioned you use Kubernetes. How come you chose that as a base technology for your development?
So can you repeat the last part?
How come you chose Kubernetes over just AWS?
Why Kubernetes?
Why? Well, basically because we were using Kubernetes in McLaren, and it was quite useful to run any pod. So in Kubernetes you have pods, and you can assign very easy a Docker container and assign some CPU and memory, and you can increase the replicas. So one of the features of the platform is that you can scale any type of pipeline. And if you use this scalability of Kubernetes plus the scalability that Kafka gives you with the partitioning, so it's a good combination to scale very quickly any of these pipelines. So Kubernetes with just one number, and in our UI is just a slide, you can say, I want one replica or I want 1,000 replicas. And this scalability is what we try to find here. So you create a one pipeline, but later if you want to scale to more devices, it's just move a slide or do auto scaling. And I think that Kubernetes is some technology that I don't know anything else to use, to be honest.
There was one last question.
So the question is about latency in the stack. So you talked about algo training and obviously application that kind of world. But what's the kind of limit to what you can get in low latency out of Kafka? Because in some cases you might be looking microseconds or 1 or 2 milliseconds.
Yes.
What do you see in the
So I think that Kafka itself is introducing around 10 milliseconds of latency. To this you need to add the latency of the network, but this depends of your infrastructure. But Kafka itself, the minimum that you will get is 10 milliseconds. Yeah. Yeah. So the SDK is allowing up to nanoseconds. So we are playing time series data with nanoseconds, but the latency itself that you will get from a real event in the world until you process it, I think that the less than 10 milliseconds is not going to be possible. But to be honest, the problem is more the network and the light speed that you know.
Okay, I think that's it for us for today. So thank you very much for attending. And we're going to be around if you want to talk.